Okay, good morning and welcome to lecture 6, still working on electronic structure methods, and today in particular I will finish up our introduction of the Hartree-Fock methods, if you want, the cornerstone of quantum chemistry, really developed in the late 20s. We have Douglas Hartree here from the University of Cambridge and Fock, I think from the University of St. Petersburg. And then we'll also go into density functional theory that in many ways is a much more recent approach. The theory itself was developed in the 60s by Walter Kohn in collaboration with Pierre Hohenberg and in collaboration with Lou Sham. But really I would say it's only in the mid-70s and then really in the mid-80s that it started to take off as actually a practical approach to study the electronic structure, especially of solids, and has become very popular to the point that the Nobel Prize for Chemistry in '98 was given to Walter Kohn for DFT and John Popol, a quantum chemistry, for the development of quantum chemistry methods. Let me remind, before we go on into the lecture, the sort of two main conclusions of last class. The first one was the appropriate matrix formulation of the Schrödinger equation. That is something that is very powerful and very useful when we actually need to solve a differential equation on a computer. And sort of the hypothesis there was that we had chosen a basis set that I indicate here with phi that would be the basis set in which I would expand my ground state wave function. And so once a basis set is chosen, it could be sines and cosines with different wavelength, could be localized wave functions like Gaussians, it could be just points on a discrete grid. But once my basis set is chosen, and once I know what is my electronic structure problem, that is, once I know what is the potential in my Hamiltonian operator, these integrals are just numbers. So solving the Schrödinger equation, that is finding the E eigenvalues and the corresponding eigenvectors, is nothing else than solving this linear algebra problem, where again these coefficients here form a vector that really gives me what are the terms in the expansion of my wave function in terms of the orthonormal basis. And as solve linear algebra problems, we have a matrix here, and it will have, if it's an order n matrix, n values for which its determinant is 0, and those are the eigenvalues for which we can find a solution. So this is important not only in electronic structure, but in a lot of applied computational approaches. And the other very useful principle here that I've listed is the variational principle. That is, again, it is possible to define a functional, that is, if you want, an algorithm that takes as input a generic function and gives us output a number, and the functional that we use is the functional that I've written here with the integral expectation value of the Hamiltonian on an arbitrary wave function divided by basically a normalization term, and it can be proven, and it was given to you as an exercise, that this quantity is always greater or equal than the ground state. And this is very powerful because if we have no idea on what the solution for our ground state problem is, well, we can just try out a few, and our best solution, although we will never know if it's the exact one or not, will be the one that gives the lowest expectation value for this term. And you know, here is a sort of example on how we could actually go on and try to solve a sort of very simple problem, that is finding the eigenstates and eigenvalues for a hydrogen atom using the variational principle. And instead of trying actually sort of different wave function at a time, what we can do that is very meaningful is choose a parametric form for the wave function. So you see, I'm writing here a generic wave function that decays as an exponential as a function of the r distance from the nucleus, from the center of the electron. So if you wanted this parameter here, alpha, determines how steep the decay of this wave function here. So by writing it in this way, I'm not considering anymore just one wave function, but I'm considering an entire family of wave function with different decays. And so what I can do is try this family of wave function, and so what I would do is stick this expression in this expectation value, and then actually the constant c is what we call a normalization constant. It always cancels out, you see, from the integral below and the integral above. This c square would just go away. And so overall, the variational principle and the expectation value is a parametric function of alpha. And the optimal alpha will be the alpha that gives me the minimum value for this number. Again, we can't go below the ground state for this expectation value. So the lower that we can go, the better. And if we use this particular choice of wave function, and this is, again, a sort of very simple analysis problem that you could actually sort of work out by yourself. I've actually written here all the terms, the normalization integral, what is its value as a function of this parameter once you do properly in spherical coordinates, considering that this is really the radial distance, and this is the expectation value of the kinetic energy, and this is the expectation value of, you see, minus 1 over r, that is the potential for the electron in the field of a proton. And if you minimize this expression, very easy, what you obtain is alpha equal to 1. So the optimal solution has an alpha equal to 1. It turns out that, you know, by solving directly the differential equation, the Schrödinger equation, we actually know that this is exponential of minus r is actually the exact solution. And so what happens in this case is that this parametric family of wave function has the right form. That is, it contains actually the exact ground state among all its possible forms. And that exact ground state is reached when alpha is equal to 1. And the variational principle will give us alpha equal to 1 without having any need of solving the very complex radial Schrödinger equation that I sort of shown at a certain point in the class on Tuesday, where we really need to solve for the spherical harmonics and sort of find out Legendre polynomial, Laguerre terms in the radial part, and so on and so forth. So this becomes very simple, and for this reason the variational principle is very powerful. And we'll actually see how Hartree and Fock used that to find out a way to tackle the problem of many electrons interacting. Because up to now we have really only thought at the problem of one electron in a potential, but the problem of many interacting electrons increases its complexity very quickly. So I'm just sort of showing here what would be, say, the Schrödinger equation for a 2-electron atom, say something typically like the atom of helium. You have a nucleus that has really 2 protons, and then you have 2 electrons around the nucleus, sort of going around. And so what is the Hamiltonian, the quantum mechanical Hamiltonian for this problem? Well, what we have is the kinetic energy terms here. So we have a Laplacian that is a second derivative in space for each one of the coordinates. So you see, this is the wave function. The wave function is an amplitude that is a function of the combined position of R1 describing the first electron and R2 describing the second electron. So you have these 2 second derivatives, and then there is a term that deals with the attraction between electron 1, say this electron here, and the nucleus. We have an attraction term here, Coulombic attraction, that goes basically as 2 over r, or z over r if we think at a nucleus having charge z. And so there is attraction here of the first electron to the nucleus, and then attraction of the second electron to the nucleus. And then the last term is actually a repulsive term, so there should be actually a plus sign here, between the 2 electrons. And so you see, it depends, again, Coulombic repulsion between the electrons on the distance between R1 and R2, the instantaneous position. So you see, this is how the Hamiltonian becomes in the case of an atom that has 2 electrons, and sort of I written here the final generalization. still for one atom, but with many electrons. So in the case where, again, you have a nucleus with many electrons orbiting around, what you will have is that a wave function that is a combined amplitude of n different spatial variables. So if we have, say, an atom like iron that has 26 electrons, well, that psi, that wave function, is a combined amplitude of 78 coordinates. And the Hamiltonian operator, again, has a second derivative for each electron in there, as an attractive term for each electron that is attracted to the nucleus that now has a charge Z equal to 26. And then each electron, so this sum I goes over each electron will be repelling each other electron. So there is a overall repulsive term. And we actually call this term here, this is the difficult term, we call this term here a two-body term because it depends on the simultaneous position of two electrons. While if you want, the first terms here are called one-body term because act only on one electron at a time, quantum kinetic energy and attraction. And truly, this Schrödinger equation becomes overly complex already by the time when we have two electrons. So we can't solve analytically even the helium atom. Okay, we can solve everything about the hydrogen atom, and we can solve the Schrödinger equation for a number of very simple problems. But already for the helium atom, we can't do that. And so in the 40s and the 50s, people developed variational approaches. They were making an ansatz, an hypothesis on this wave function, expanding this wave function in a series of other functions depending parametrically on a number of coefficients, 2, 3, 5, 8, 200 coefficients. And the more coefficients there were, the more flexible that wave function was. And so systematically, by adding more and more flexibility, you could go lower and lower, and hopefully you were converging. And say for something like the helium atom, well, sort of, you know, the total energy of two electrons in the helium atom is something like 5.8 Rydbergs. And you could get sort of, you know, very, very close down to a fraction of 100 of an electron volt just by 3 or 5 parameters. But then as you go to more and more electrons, the problem really has a complexity that explodes. And in all of this, I want to remind you, I'm not using anymore the international system of units, so I'm not using meters and seconds, but I'm using what are called atomic units. And there is a handout on your Stellar web page reminding that the unit of energy is what we call the Hartree, that corresponds to another set of units that are often used. Say a Hartree corresponds to 2 Rydberg, and the Rydberg is 13.6 electron volt. An electron volt is the energy of an electron that sort of feels a potential difference of 1 volt, and 1 electron volt is often considered 23.05 kilocalories per mole. In the sort of electronic structural literature, you'll see all these numbers. Often chemists use the kilocalorie per mole unit. Physicists tend to use the electron volt. And again, I remind you that sort of, you know, the average kinetic energy of an atom at room temperature is 0.04 electron volts, and the binding of a water dimer is 0.29 electron volts. So the electron volt is really the order of magnitude of the binding of sort of weakly attached molecules. Okay, so now the problem, and that's where the sort of Hartree and Hartree-Fock solution become important, is to deal with realistic system. That is, we need to deal with molecules, or we need to deal with solids. So we need to deal in principle with a Schrödinger equation in which we have a lot of nuclei. I'm sort of denoting here with capital R the position of the nuclei. Again, if you want to find out what is the structure of benzene, or if you want to find out what is the electronic structure of silicon, you need to keep in mind that, say, for benzene, you will have 6 6 Coulombic attractive centers that are the 6 carbon nuclei in a ring, and also the 6 1/r protons around. So the position of those nuclei determine what is the potential acting on your electrons. So in principle, the sort of Schrödinger equation will be something like I written here. But we can make this fundamental simplification that will always be the case for the classes that follow. That is, we never treat the nuclei as quantum particles. Okay? In principle, also the nuclei are quantum particles. So they would have their own wavelength. They come in as variables into the wave function, and you would need to calculate, say, things like the quantum kinetic energy of the nucleus. That is the Laplacian, the second derivative of the overall wave function with respect to the nuclear coordinates. In practice, remember the Broglie relation, the nuclei are so heavy that their wavelength is very, very small, so we can truly treat them as classical particles. And the electrons are so much faster than the nuclei that even if the nuclei move, the electrons can always, much faster than the nuclei, follow this movement and reorganize themselves as to being in the lowest energy state possible. Basically, you have to imagine this picture of the molecule vibrating at room temperature, and the nucleus then will have a kinetic energy. All the mass of the molecule is in the nuclei, so all the effects of temperature, if you want, are in the vibration of the nuclei, but these vibrations are very slow from the point of view of the electrons. So the electrons see these nuclei slowly moving and rearrange themselves as to being in the ground state for that instantaneous configuration of the nuclei. Obviously, if the nuclei starts moving very, very fast by any chance, well, then the electrons can't do this. They can't follow anymore. And so if you want, you can start having electronic excitation. That is, the electrons are not anymore on the lowest energy state possible for that given configuration. That doesn't really happen, especially if we are just considering a molecule or a solid at room temperature, but it could happen, say, if we have an external potential that changes very fast. If we shine a laser light on a molecule, then light is nothing else than an electromagnetic field, and laser light will typically have a frequency that is fast and comparable to the frequency of the electrons, and so all this adiabatic approximation break down, and lo and behold, we can actually excite with a laser the electron in a higher energy state. But for what you are seeing in this class, we'll always think at electrons in their ground state. This is what people call often the adiabatic or the Born-Oppenheimer approximation. These two terms, in most cases, are used in the same way, although sort of chemists tend to make a subtle distinction about what adiabatic means and Born-Oppenheimer means. And adiabatic really refers to the coupling between sort of the different potential surfaces for the electrons depending on the velocity of the nuclei. And Born-Oppenheimer implies that there is no influence of the ionic motion of one single electronic surface. But I mean, this is fairly technical. Just remember that sometimes these two terms actually mean something very different and very specific. Okay, so this is now becomes our most general expression for the Hamiltonian, and so also for the energy of a set of nuclei and a set of electrons. That is really our picture of a molecule or a solid. And again, we will have the nuclei generating Coulombic attractive potentials in every position where they are. So there is what we call an electron nucleus term that is an attractive term in which we have a sum over each and every electron, because each and every electron feels the potential of all the nuclei, and the sum over all the nuclei refers to a sum of z over r terms. So in whole space, wherever there is a nucleus, there is a 1 over r term, and this sum over nuclei is the overall potential for the electronic system, and each electron feels this potential. And this is the fundamental attractive term. So electrons are attracted to the nuclei, but also electrons repel each other, and this is the other term. So you see, each and every electron has a charge 1 in atomic units, and there's a Coulombic repulsion with each and every other electrons. And then, of course, for each electron, we have the sort of quantum kinetic energy here. And so I've listed here in the Hamiltonian all these terms. We have the quantum kinetic energy here, we have the electron-electron repulsion, and we have the electron-nucleus attraction. And then there is a last term that is truly a classical term because it involves only the nuclei, and so it's a repulsive term that is the nucleus-nucleus repulsion. So if you want to think for a moment at a hydrogen molecule, say, what you would have is a nucleus, another nucleus, and then a wave function of all the electrons around. And there is a classic term that is the electrostatic repulsion between the two nuclei, and there is a quantum term of repulsion between the electrons and an attraction between the electron and the nuclei. And basically all these sort of electrostatic terms, nucleus, nucleus, electron, nucleus, and electron, electron, almost balance themselves. Each and every one is very large, but then the combination of these three almost cancels itself out, and that's why actually the binding energy of a molecule is much, much smaller than any of the energies, say, of two charges at that distance repelling each other, or even just the energy of a core electron very close to its nucleus. And that's why also electronic structure calculation are very delicate, because what you need to find out is a total energy that is the combination of terms that largely cancel each other out. And so you need to be very accurate in order to actually decide if something like a hydrogen molecule binds together or sort of breaks apart. Okay, now this is truly a problem of great computational complexity. And as I said over and over again, we can't really deal, even computationally, with an object that has all the information content of a wave function. So let me actually go through this into the next slide, in which I sort of written out explicitly the example of the iron atoms that has, again, 26 electrons. So the electronic wave function will in itself have 78 variables. And if you think at how many numbers do we need to store this object with any kind of precision, well, suppose that we even limit ourselves to a very, very coarse sampling, only say 10 values around the iron nucleus. Well, even to give this wave function, to give this amplitude with this very coarse sampling, we would need 10 to the 78 numbers. So basically there is no way we can numerically deal with the complexity of the wave function. And this is where sort of the power of the variational principle and the ideas of Hartree-Fock came together. And sort of, we'll first discuss the first idea of Hartree in dealing with this problem. Remember, what we have is a set of interacting electrons. And, I like to sort of compare each one of you to an electron. So what you need to think and what the complexity of this problem is that at every instant in time, each one of you is sort of interacting or actually repelling with each one else. So this is the complexity of a many-body problem. In order to sort of understand what's happening, each thing needs to know what everyone else is doing. And Hartree introduced the concept of independent particle and effective potential. This is something that comes over not only in electronic structure, but it comes over in a lot of problems where we actually need to deal with a very large number of interacting elements and interacting particles. And sort of the general idea is that we can approximate and try to solve this problem by not considering what each electron instantly does, but we can solve the problem by treating what one electron would do in a field that on average represent what all the other electrons would be doing. So if we want to think, say, what I would be doing, I shouldn't try to find a solution that instantaneously knows about what each and everyone else is doing, but I could try to find a solution for myself interacting electrostatically with the average charge distribution that everyone else does. So instead of sort of having to know what is the instantaneous position of all the other interacting electrons, I could make a sort of an approximation that I could actually really just try to deal with the way I interact with an average distribution of everyone else. So this is, if you want, the concept of mean field or effective potential. We are sort of averaging over all the variables. And there is actually a sort of mathematical way to do this that I'll introduce in this moment. But if you want, the Hartree solution really leads to this, leads to a Schrödinger equation in which we are actually trying to solve the problem of a single electron at a time, but that electron fills the average electrostatic charge distribution of all the other electrons. And one can actually obtain this directly from the variational principle. That is, one can make an ansatz for the wave function. What is written here is, this most generic wave function, and one can make what turns out to be actually a fairly severe approximation. That is, we can say that this many-body wave function can actually be written as a product of single particle orbitals. So you see what's happening when we are actually making this hypothesis is that varying R1 will change the amplitude of the wave function independently from what happens to R2 and Rn. These have all become independent variable. There is no combined effect what R2 and R1 are doing, say, or any couple or any triplet, and so on and so forth. So if you want, if we sort of fix all the other variables, we can independently look at what each one of these orbitals is doing. And you can think, just what would come from a Taylor expansion. This is an approximation. It's not a true solution. Okay. Suppose that we were dealing with two variables. Well, I mean, something like think at a generic wave function that could be written as, say, the exponential of the square root of R1 plus R2. That can't be decoupled in the product of two wave function. So the product of two single particle wave function is something simpler that doesn't capture the complexity of all the possible two-body wave function. And so in this, it's an approximation. And so Hartree made this approximation and then asked itself, what happens if I actually throw this approximation in the variational principle? Now, the difference is that instead of having just a function that varies parametrically, now what we can really vary in our variational principle are the shapes of all these sort of single particle orbitals. So what we are asking ourselves is a wave function of this form thrown into the variational principle will give me condition that each of these orbitals need to satisfy. So if you want, you really need to now calculate sort of with functional analysis what are the differential equations that each of these orbitals, phi 1 to phi n, needs to satisfy so that the overall expectation value of the energy is minimum for a wave function written in this restricted class of product of single particle orbitals. And so when you actually work out the sort of fairly complex functional analysis of this problem, that's actually described, if you're interested, in one of the references that we have given you, the Branston and Joachim book on the physics of atoms and molecules. What you obtain for the specific case, again, of a Hamiltonian operator in which the potential is given by a linear combination of attractive Coulombic potential is a set of equations. That is, what you obtain is a new set of differential equations instead of having, if you want, one single Schrödinger equation for a many-body wave function, what you obtain if you are dealing with n particle is n different differential equation, each one being a differential equation for only a single particle wave function. This is still fairly complex, but the complexity of this has gone from, being a complexity of a wave function of 78 variables to, say, the complexity of 26 equations in 3 variables each, if we are sort of working in 3 dimensions. And actually, the form of this equation is very intriguing, because this really looks like a Schrödinger equation for one electron. You see, here is the quantum kinetic energy term for this electron, and then there is the interaction between this single electron with the Coulombic distribution of nuclei, and then there is a term. You see, this appropriately is called the Hartree term, in which this electron I is actually filling a Coulombic repulsion, this is the Coulombic term, of a charge density distribution. Remember that if we take the square modulus of a wave function, we obtain the probability of finding an electron somewhere. And the charge density is nothing else than that, is the probability of finding an electron somewhere. And so you see what we have is, for the electron that we have denoted as I, the interaction between the wave function and, as usual, a potential, in which we have the Coulombic term, and the repulsion, the Coulombic repulsion, is between the electron I and the charge density distribution of each and every other electron j. So you see this sum goes over all the other electrons. So my many-body Schrödinger equation has become a series of equations that we call single particle equation, a differential equation for each and every electron. And those differential equations that, as I said, have been obtained formally just by applying this ansatz to the variational principle, are in the form of a Schrödinger-like equation with a kinetic energy, an attractive potential, and now we have only a mean field interaction between the electrons, because electron I doesn't instantaneously need to know what each and every other electron does, but it actually only interacts with the average charge density distribution that is given by the square modulus of J. Okay. So this is a great simplification, and it actually allowed some of the first calculations, say, on atoms. Actually, sort of this was developed in the late 20s, and very quickly it was realized what was wrong, and we'll see that in a moment. That is sort of the lack of correlation, because there is a specific rule that electrons are fermions. But really, this was sort of the first time in which we had sort of workable differential equation for a many-body system. And the most important conclusion of this, and sort of, where the complexity of the many-body problem comes back in, is that this new operator, this new overall Hartree operator acting on the wave function, has become, as we say, self-consistent. That is, the operator itself depends on what the other electrons do. So it depends on what the solution to all the other differential equations are. So if you want to know what electron I does in the mean field of all the other electrons, you need to know what is the wave function of each and every other electron. But in order to solve what the wave function of each and every other electron, you will need to know also what electron I is doing. And so really, this is very different. The Hamiltonian operator here is not anymore given at the beginning of the problem, but actually needs to be found, because the operator, the action on one electron, depends on what the other electrons do. And in order to find out what the other electrons do, we need to solve the set. So this set of, say, the case of iron, again, 26 differential equations need to be solved simultaneously. Okay, so we actually solve it iteratively. We start with a guess for what the wave function would be, and we try to find a combined solution. I'll describe in a moment what the algorithm is. But so this is how the many-body complexity comes in. That is, we need to solve a differential equation for which we don't even know at the beginning what is the operator acting on our single particle wave function. And so the concept of self-consistency and of iterative solution will basically be always present in all the electronic structural approaches that we are going to see in this class. And it's actually very simple to sort of figure out what could be an actual algorithm to try to get to the solution. That is, we need to start with an arbitrary guess for all those 26 orbitals. And once we have that arbitrary guess, we can construct the charge density of every electron, and so we can construct what would be the operator acting on each one of the phi I. That is, we can construct this term here. Once now we know what actually our differential equation is, we can solve it. So we find what are the ground state of each of those 26 differential equations. And now with those ground states, we can construct again a charge density of each and every single electron. We put it together. We have a new Hartree operator, and we can solve these differential equations again. And we keep iterating this until what we obtain is a Hartree operator in each differential equation that doesn't change anymore. And so we have now a set of self-consistent orbitals. In most cases, you actually don't get to convergence. So a lot of the algorithmic advances that sort of has been done in electronic structure has actually to do with this problem. That is, we need to find ways to get this procedure to converge to an actually self-consistent point. But the concept is all here. And if you want, sort of the simplest thing that you can do to make sure that sort of you are going to iterate to self-consistence is to move very slowly. That is, whenever you have sort of a set of solution, you don't want to construct your Hartree operator is new charge density with this solution, but you want just to modify a little bit your previous charge densities to go in the direction of the new charge density that you were calculating. So you somehow try to minimize the change in the operators from one iteration to the other, and that tends to be actually sort of fairly functional in a lot of problems. Now, Hartree was a very interesting character, sort of, again, growing up in Cambridge, sort of turn of the century. He sort of became an expert in differential equation during the First World War, because basically people had the problem of sort of, sending cannonballs across the lines, and so that there was a lot of differential equations. So sort of mid-20s, he developed this sort of general idea of the Hartree equation that are really what we call coupled integral differential equation, because there are derivatives and there are integrals. And so what you need to do is now solve this equation that can't really be solved analytically. And luckily, sort of, that was the time in which people were developing, if you wanted, the first computers. No electronic in there, so computing machine, but mechanical. And sort of one of the first computers was at MIT. This is actually a picture from the MIT archives. There was an electrical engineer named Vannevar Bush, to which Building 13, the Bush building, is named, that had developed one of the first mechanical differential equation solvers. And so Hartree came at the end of the 20s to MIT to actually solve the Hartree equation, I guess in some building here, exactly on that machine, and then went back to Cambridge. And so this, I thought, was an interesting note. So what do we obtain when we actually solve the Hartree equation? Well, the most fundamental concept is that we are losing some information on what's happening instantaneously to all the electrons. This is what we call, sort of generically speaking, a correlation, and I'll give you the technical definition in a few slides. But basically, this is what's happening. Let's consider sort of the case of the helium atom. That is sort of the simplest case in which you have more than one electron. So what you have is two electrons. What does the Hartree equation tell us about, or what do the Hartree equations tell us about these two electrons? Well, we have two equations, and in each of them, one electron, okay, is going to feel an average electrostatic repulsion from the other electron. Okay, so what we have is that this red electron here is attracted to the nucleus and is repelled by a sort of, spherically symmetric average charge distribution. Okay, so this is what's happening. This is what Hartree tells us. But in reality, electrons instantaneously try to keep themselves as far apart as possible, okay? Because electrons repel each other. So in a sort of simplified way, you could think at electron 1 and electron 2 trying to orbit the nucleus as much as possible in opposition of phases, okay? So the true two interacting electrons try to be as far as possible at every moment in time during their evolution around the helium nucleus. But this instantaneous correlation, that is the fact that in sort of the wave functions tries to keep the electron as far as away as possible, is lost in the Hartree equations because what we do is we are really having one electron interacting with the average position of the other electron. And so in the Hartree equation, there are a lot of terms that have to do with our initial electron red being too close to the green charge density distribution. So if you want the wave function, that is the overall solution of the Hartree equation, tends to have too much electrostatic repulsion between electron 1 and electron 2, and that's why ultimately the energy of this Hartree wave function is higher than the true solution. This is what is missing in the Hartree equation. The fact that what you want is a lot of correlation, that is, electrons want to keep each other apart as much as possible, but that, if you want, is really an instantaneous solution, is what people call dynamical correlation. Electrons want to keep apart from each other, but if you start looking at a mean field solution in which only one interacts with the average charge density, you have lost the possibility of sort of having this sort of instantaneous non-symmetric distribution. And so in general, this is what we call correlation, and this is what is missing in the Hartree picture. There is another sort of very fundamental concept that I'll describe in a moment, that the wave function, the ansatz for the Hartree wave function doesn't satisfy a fundamental rule for wave function. We say it's not antisymmetric, and I'll show you in a moment what it is. That is, if you want, it doesn't respect a fundamental constraint on the shape of wave function. And so that's, if you want, an error, and that's another sort of source of error in our final estimate of the energy. And in particular, what it doesn't do, it does not remove what is sort of the accidental degeneracy, the fact that there is the same energy for electrons that have the same principal quantum number n and the same angular momentum number L. But really what is most important is this lack of a physical constraint and this lack of correlation. Very soon, I mean, sort of probably the same here on a year later, Hartree and independently Fock realized that one could actually find a better solution to the problem, sort of satisfying one again of the sort of fundamental rules of nature that had been discovered in the 20s during sort of the development of quantum mechanics. And so this, one of these rules was what is called the spin statistic correlation. And sort of this is really very general. First of all, there is a sort of division in elementary particles that says that all elementary particles can be called either fermions or bosons. And so things like electrons are actually fermions. They have a half-integer spin. But there is a sort of fundamental difference between fermions and bosons. And in particular, and sort of they satisfy different statistical rules for an ensemble of many interacting electrons or for many bosons. And these rules, this is nothing else that, again, another rule like in classical mechanics, you have Newton's equation of motion. In quantum mechanics, you have a rule that a wave function that describes fermions, that is a wave function that describes electrons, needs to have this overall shape. That is, it needs to change sign when we invert two variables. Okay, so we have this general form for the wave function. We exchange two variables, and what needs to happen is that the wave function needs to change sign. And this has something to do. This can actually be demonstrated, but it's sort of what people call quantum field theory. So it's a sort of advanced concept, but it's a very simple rule, and it's a very simple symmetry of the wave function. In the same way, if you want, you have, in a crystal, you have physical symmetries for what could be, some of your properties, like an elastic tensor or a piezoelectric coefficient. Well, what you have is a fundamental symmetry for a wave function describing electrons. It needs to change sign when you invert the two coordinates. And so what the Hartree solution didn't have was exactly this anti-symmetry requirement. So remember, the Hartree solution was just the product of single particle orbitals. But Hartree very quickly realized that, you can actually sort of satisfy this symmetry requirement if instead of taking just the product of n orbital, you take the sum of the product of n orbitals, where you interchange the variables in all the possible ways, putting a plus or minus sign in front depending on how much interchanges you had. And I think it's very simple to think at this problem if you have, say, only two electrons, so you have only two orbitals. And so we could call these two orbitals, say, alpha and beta. And so what we would have is the Hartree solution that is the product of the alpha orbital function of the first R variable and the beta orbital function of the second variable. And this doesn't change sign if we exchange 1 with 2. It becomes a different function. It doesn't become the same function with a sign changed. But you can see that what we can do without increasing really the complexity of the problem, that is still dealing with just the need of describing two orbital, what we could do is take as an ansatz for the wave function describing two electrons, something that is actually alpha 1 B2 minus B1 alpha 2. Okay, so we have still two orbitals that we need to figure out. We need to figure out what is the shape of alpha and what is the shape of beta. But now we are using as an ansatz for this two electron wave function something that actually changes sign when you exchange 1 with 2. Okay, so this is the trial wave function of Hartree, and this is the sort of trial wave function of what we call the Hartree-Fock method, that is basically a trial wave function that has built in anti-symmetry constraint for exchange of particles. And this can be generalized to the case of n particles. And really, what we call a sum of n term with all the possible permutation, with all the possible signs, is nothing else than a determinant. If you think at what a determinant is, well, this determinant is going to have one element is going to have a sum of terms that each of them are written as one term from each column, and we are taking all the possible permutation, and we are taking a plus sign or a minus sign in the sum of all these terms, depending on how many permutations they are. This is just the sort of linear algebra definition of a determinant, and you see again a determinant of two functions is just what I written here in green. I'll write here in a corner, if we are asking what alpha 1 determinant, beta 1, beta 2, and alpha, beta 1 and alpha 2, and beta 2. Okay. So this would be the sort of specific expression of this determinant for the case of two particles, and if you just solve that determinant, you have only these two terms. So we haven't increased in going into the Hartree-Fock method the complexity of the problem that we need to solve, because we still need to find n functions where n is the number of electrons, and we need to find now the appropriate differential equation that descend from the variational principle once we stick this determinant into the variational principle. And again, it's not very complex functional analysis, and the Bransden-Joachim describes that in detail. But with this new solution, with this new ansatz, what we find is a new set of differential equations that look a lot like the Hartree equation that we had written before. I'll go back to this in a moment, but have an additional term. So what we find are, again, single particle equation. So we have an integral differential equation for each single particle orbital lambda that is written in red. And now what we have is a sort of additional term. So we still have the quantum kinetic energy for that electron, and we still have the interaction between that electron and the collection of attractive Coulombic potentials. We still have the Hartree electrostatic term, in which electron lambda interacts with the charge density phi star mu times phi mu of every other electron mu, and I'll come to what goes into this sum in a moment, but basically we have electron lambda interacting with the charge density of electron mu, and obviously it's a Coulombic electrostatic repulsion, so there is a 1 over r term. But now there is a new term with a minus sign that comes out only from the anti-symmetry requirement, okay? And that is what is called the exchange term, and is the new player in the Hartree-Fock equation. And it's a little bit exotic, because if you want now, we don't have anymore an operator that could be, say, a local operator, a charge density distribution acting on an orbital, but it's really become a non-local operator, because the orbital on which I'm acting has gone inside the orbital sign. Okay, so this new term here that we call the exchange term is a purely quantum mechanical term that comes out exclusively by the anti-symmetry requirement on sort of what happens to a fermionic wave function when we invert coefficients. And there is another sort of fundamental distinction between the Hartree and the Hartree-Fock equations. This sum here, you see this sum over mu, in the Hartree equation was running over all the electrons but the one that we were considering, okay? And now instead, this sum mu is running on all the possible electrons. So what you have in this term here is what is technically called self-interaction. Suppose that for a moment you were trying to solve the hydrogen atom with just one electron. Well, what happens in the Hartree equation for the hydrogen atom, there is obviously no exchange term, and there wouldn't be also no Hartree term, because in the Hartree equation that you have seen before, what you have is a sum over all the other electrons, but there are no other electrons, so this term is not there, and what you trivially recover is the single particle Schrödinger equation for the hydrogen atom. In the Hartree-Fock equations, now even for the hydrogen atom, what you have is that now you have this term. You have actually an unphysical self-interaction. That is, you have electron 1 interacting with itself, and actually not interacting with itself in a sort of local way, but it's interacting with its own charge distribution. This is actually a sort of unphysical thing, but what happens exclusively in the Hartree-Fock formulation is that there is a second term. There is the exchange term, and the exchange term, you see there is a minus sign, cancels for the hydrogen atom the self-interaction term exactly. If you just think, if you have only one electron, you have that there is only one phi, so the lambda goes away, the mu goes away. So here the electron is interacting with its charge distribution, but then this term here, just remove all the sum and remove mu and lambda, is cancelled out thanks to the minus sign by the exchange term. So Hartree-Fock formalism is actually what we call self-interaction corrected. Okay, an electron, even if it's a mean field picture, doesn't interact with itself. And that's actually a very beautiful symmetry property that other approaches like density functional theory do not satisfy. And truly, a lot of the problems that come out in density functional theory that otherwise perform really well have to do with this self-interaction problem. And so those problems are very significant if you think for a moment at problems like dissociation of a molecule in atoms. So when you really sort of consider how, and we'll discuss this in detail, how the energy changes along a process in which the electrons needs to localize itself from a shared bond to a localized bond. And that self-interaction problem kills density functional theory and would actually not be present to begin with in Hartree-Fock. So this is actually very important. There is another thing that actually the Hartree-Fock equation have a beauty in the fact that the operator acting on the single particle orbitals does not depend on which orbital you are looking at. Because here we have a sum over all the states. So this does not depend on which electron you are looking at. That's different from the Hartree equation. In the Hartree equation, there is a Hartree term where this sum would exclude the electron itself. So the Hartree equation are actually more complex to solve because the electron, the operator, changes depending on which electron it's acting. While the Hartree-Fock equation have the same operator. And so what we really need to find out if you are solving the iron atom, what are the 26 lowest energy solution for all the electrons in here. So that's sort of a very good thing, but there are terms, there are integrals that are actually very expensive still to calculate. And ultimately, it's terms like this that gives us the scaling cost of the equation. Often what we solve an entire structure problem, we want to know what is its scaling cost. That is, how much our calculation becomes more expensive, say, if we double the size of the system, because that basically tells us how large we can go. And because of sort of, these integrals that sort of involve 3 orbitals, and the fact that then to calculate an energy you have one more sum, really the scaling cost of the Hartree-Fock equations in principle goes as the 4th power. So if I'm studying a system with 2 electrons and then I want to study a system with 4 electrons, well, the cost has gone up 16 times. And a 4th power, like any power, kills you very rapidly. So that's why we can study, a molecule like benzene with Hartree-Fock, but we can't study really something like DNA with Hartree-Fock, or really none with the standard electronic structure methods. And a lot of effort actually goes into developing linear scaling methods. That is, methods in which the computational cost of your calculation doubles if you double the number of electrons. And at the end, nature is linear scaling, because really you can imagine that the wave functions of the electrons here doesn't have anything to do with the wave function of the electrons there. So there is really, when you go far away, no exchange of information between sort of wave functions in different points of space. And so there is ultimately a linear scaling nature, but sort of, our algorithms in general are not yet there. And we'll discuss a little bit in the sort of some of the later classes how to solve this problem. Before sort of going on, I wanted to show one sort of very simple conclusion, actually, of having a wave function with the proper symmetry, that is, having a wave function written as a slated determinants, because that form gives us automatically what is called the Pauli principle. If you remember what the Pauli principle is that you can't have two fermions, two electrons in particular, in the same quantum state. So you can't have two electrons having, say, the same orbital. And that's obvious because in a determinant, two electrons having the same orbital would mean that two columns in the determinant are identical. And when two columns in a determinant are identical, the determinant is sort of linearly dependent, and so the solution is 0. Okay. So a lot of good things came out of Hartree-Fock. In particular, one could start solving atoms, and one would recover, say, the shell structure of atoms. So if you would sort of, obtain the Hartree-Fock solution for something like an argon atom, and then, say, plot the overall charge density of the system, well, it would start to look like this as we move from the center outwards. So it would clearly show the fundamental sort of periodic table nature of things. That is, it would show a 1s shell, and then it would show a 2s and a 2p shell. And this is something that some of the other approaches, like the Thomas Fermi approach that we'll see in a moment, that were being developed at the time, didn't have. In general, Hartree-Fock is very good to describe atomic properties. And what is most important is a well-defined approximation in the variational principle. Remember what sort of, one of the fundamental power of the variational principle is that if we make our wave function ansatz, our trial wave function, more and more flexible, we become better and better. So Hartree-Fock is a certain sort of hypothesis and gives us certain energies. But what we can do is make our wave functions more and more flexible, write them not only just a sort of single determinant, but a single determinant plus something else. And the solution that we'll find will be sort of computationally more expensive to find, but is going to be better. So Hartree-Fock, in principle, can be improved indefinitely. That is something very powerful conceptually. It's practically very complex, because those costs that were scaling already in simple Hartree-Fock, like the fourth power, keep going up. What you'll see in density functional theory is that besides being a theory that tends to sort of give more accurate results for a lot of physical properties, it's something that also scales a bit better. It scales as the third power of the size, but it's a theory that can't really be improved in any systematic way. One can sort of find ingenious way to make it better, but there isn't a brute force improvement strategy like there is in Hartree-Fock. The Hartree-Fock operator included the last term that we have called the exchange term. And so for every possible atom, for every possible molecule, for every system, there is a well-defined Hartree-Fock energy. And this Hartree-Fock energy is going to be good or very good or sort of so-so, but it's always going to be higher than the true ground state energy of our system. And actually, what is technically called the correlation energy is the difference between the true energy of your system and the Hartree-Fock energy. So when people talk about correlation energy, they refer to all that energy that is not captured by an Hartree-Fock approach. And in that sense, it's a well-defined quantity, although it involves a generic term, correlation, that can mean a lot of things, and I'll show you a few examples. There is sort of one more thing that we can do. We have sort of never discussed up to now spin, but in reality, an electron is described by a wave function that doesn't have only a space part. So in order to describe an electron, we don't only describe what the distribution of its wave function is in space, but we also sort of specify what is the spin of the electron. And that sort of, has to do basically with spin being an operator that can sort of, be simultaneously diagonalized with a sort of, well, it becomes complex, but sort of, it's another quantity. You can think of it as a color. We need to specify if our electron is red or blue, or in particular, we need to specify what is its spin, what is its projection with respect to an axis. And so in this, you need to think at a wave function of an electron not having only a spatial distribution, but it has another property besides the spatial variables that is called the spin. And you can make a sort of approximation that is what is called the restricted Hartree-Fock scheme, in which you sort of decide that an electron of spin up and an electron of spin down will have the same spatial part, so the same wave function in space, and their wave function differs only because it describes an electron with a spin up and an electron with spin down. Again, this corresponds to your sort of classical periodic table picture. You're sort of constructing the periodic table. You go, say, from hydrogen, one electron in the 1s level, to helium, one electron in the 1s level with spin up, and another electron in the same level with the spin down. Actually, if you think, the periodic table itself is not a truth. It's just a Hartree-Fock picture of electrons. Okay? In principle, you shouldn't be able to talk about single particle quantities, 1s, 2s quantities, because in reality, if you have iron, you have a many body wave function that is an overall function of all the electrons. It's only when you enter into a sort of Hartree-Fock picture that you can have a well-defined concept as a single orbital for an electron and what's the energy for that electron. So if you want, what we think at these beautiful things as the periodic table is nothing else than the Hartree-Fock solution of the atoms. And again, we can make the approximation in which we fill up every orbital, every spatial part, with two electrons with the same spin. That tends to be a very good approximation for a lot of problems, say a lot of sort of bound system, and we'll see the case of the hydrogen molecule in a moment. But you could actually make your wave function more flexible, saying that, say, orbitals don't need to be paired. That is, an electron with a spin up and an electron with spin down, even if they are very close in energy, can have two wave function in which the space part differs. And this is, really an ansatz that contains this in itself. So an unrestricted Hartree-Fock solution will always give you a lower energy than a restricted solution. And we'll see in a moment an example. And this is the case, say, of the dissociation of a hydrogen molecule. So, this is, when we go back and try to understand what is the bonding between, say, two hydrogen atoms. And, we had seen in one of the first lectures, we discussed about potentials. That is, what is the energy of a system as a function of the nuclear distances. And this is what we are doing here. We are trying to look at the energy of the system as a function of the hydrogen-hydrogen distance, and there will be an equilibrium distance that corresponds to the minimum of the energy. And this is what classical potential try to do. They try to replicate what is the energy of a system as a function of the nuclear coordinates, and they tend to do very well, as Professor Sider has told you, close to the region where they have been fitted. If we have fitted a potential around here, we tend to be able to reproduce things very well. Obviously, it's very easy to sort of even find out a potential that reproduce all this curve, but when you start to have more than two atoms interacting, there are all these problems of bond breaking and bond forming that can't really be given by classical potential and can be given by quantum mechanical calculations. And so in principle, we have an ideal solution that is, if we were able, and nowadays with numerical accuracy, we are basically being able to solve almost perfectly this problem. We are able to find out what is the total energy of the system as a function of the nuclear coordinates. And then for this specific problem, the two Coulombic potentials sort of at different distances, we can find an Hartree-Fock solution, okay? And we have only two electrons. We can find a restricted Hartree-Fock solution in which we say, well, these two electrons are going to have the same orbital part in the wave function. They just differ in having a spin up and a spin down term. And that make them orthogonal, so certain things are going to happen in the exchange term. But then, we plotted this energy as a function of the distance, and this is what we have. And then we can sort of release this condition. We can say these two electrons don't need to have the same orbital part for the wave functions. They can have different parts, and we can do that calculation, and what we obtain is the unrestricted Hartree-Fock solution. And you see two sort of fundamental things coming out from here. First of all is that all these Hartree-Fock approaches give you an energy that is obviously larger than the exact energy. It's the variational principle. We can sort of, get lower and lower, but we will never be able, and that's very good, to go below the true energy. So the more flexible we make our wave function with post-Hartree-Fock methods, the more we'll be able to recover this sort of last electron volt of correlation energy. Okay, so this is all where our effort is going. But you see, Hartree-Fock is already doing extremely well in giving us the equilibrium distance. I mean, this is the Hartree-Fock equilibrium distance, and this is the exact equilibrium distance, so it's doing a good job. What restricted Hartree-Fock is not doing well is giving us the dissociation energy. Okay, so restricted Hartree-Fock works very well around the minimum, where you really should have this sort of physical picture of your ground state being given by a bonding combination of 1s orbitals. Really, this is what the covalent bond for a hydrogen molecule is the two 1s orbitals sort of covalently overlapping. And so restricted Hartree-Fock does very well here, and it's basically identical to unrestricted Hartree-Fock, but formally unrestricted will always be lower than restricted because it contains the restricted solution, because in order to sort of have a restricted solution, you just need to have the orbital part for the two electrons to be identical, but because it can also be different, it will always be lower than the restricted Hartree-Fock. And you see, when we break this system apart, okay, when we want to go from a bound hydrogen molecule to two atoms, the restricted Hartree-Fock is doing very poorly. It'll give us an energy that is a very poor predictor of the dissociation energy. The dissociation energy, the true dissociation energy of this system is the distance between the minimum here and the zero value. That is the energy that we need to spend to break apart the molecule. Unrestricted Hartree-Fock will do very well. I mean, obviously it goes to zero in this scale when we are far apart, and so we have this 1 electron volt error. But the restricted Hartree-Fock is doing very poorly. And why is that? Well, basically because the restricted Hartree-Fock is really doubly occupying the same spatial part, the same sort of bonding combination, and that's good when the system is bound, but when you break it apart, is very poor, because what you really want is, if you want in your solution, you want to mix in another determinant that is given by the anti-bonding combination. because if you think the bonding state has always a pile-up of charge in between the atoms. But when the molecule dissociates, you really want to have a solution that has zero charge density between the atoms, and that looks much more like the anti-bonding combination of 1s orbitals. And so the restricted Hartree-Fock doesn't have this freedom, so it does very poorly. And unrestricted has the freedom of having two orbitals that are different for the two electrons, and so it just puts one orbital on one atom and another orbital in another atom, instead of having a single orbital doubly occupied. And so unrestricted Hartree-Fock is going to be much better, especially for problems like the bond-breaking reactions, or for problems in which you have a sort of isolated spins. So you have atoms, you have single electrons that are not paired. There are actually a number of theorems that can be derived from the Hartree-Fock equation. I won't dwell on them. They are generically called Koopman's theorems, and they have to do with calculations, say, of quantities like the ionization energy or the electron affinity. What is the ionization energy? Is the energy that you need to spend to remove an electron from an atom, or the electron affinity is the energy that you gain when an electron captures, when an atom captures an extra electron. So how do you calculate them, say, in an electronic calculation? Say the ionization energy, well, it'll just be given by the difference, say for the case of iron atoms, of the Hartree-Fock solution with 26 electrons and the Hartree-Fock solution with 25 electrons. So you do these two calculations, you take the difference, and that will be our ionization energy. And the affinity will be the difference between the calculation with 27 or 26 electrons. But you can actually sort of do very well without having to do two calculations, but having just one calculation. If you make the hypothesis that really your single particle electrons do not change in the process. So if you make the hypothesis that in going from 26 to 25, the shape of electron 1, electron 2, electron 3 do not change, and that's an approximation, they will change a little bit. But if you make this approximation, you can actually prove that the difference between the system with 26 electrons and the system with 25 electrons, the difference in energy is just given by the eigenvalue of the 26th electron. So basically a single calculation gives you already an estimate of ionization energies and electron affinities. Although in principle you could always do two calculations, but this, if you find them, are called the Koopman theorems. What is missing in Hartree-Fock? What is this correlation that we are trying to recover? Well, often we think at it in two ways. We can sort of think at it, part of it is dynamical correlation, is what I've described you in the case of the helium atom. That is, when we have two electrons interacting, they like to keep each other as far away as possible from each other instantaneously. And because we have a mean field solution, we are actually overestimating the Hartree energy. We tend to put electrons too close to each other because you have one electron interacting with the average field of the other, and so in that energy term, you have that there are a lot of configurations in which the two electrons are too close to each other that raises the energy of your system. So we call that dynamical correlation, and these are sort of, heuristic terms. And then there is another sort of, class of sort of errors that we are making that often are called static correlations. And those have to do more with the fact that a single determinant solution doesn't have the flexibility that you need. And this was the case of the breaking apart of the hydrogen molecule. You really want, when you're sort of, breaking apart the molecule, to have a two-determinant kind of flexibility with both sort of bonding and anti-bonding combinations. And sort of all of this is missing, and we can sort of, systematically build it up, improving, say, the flexibility of the wave function. And, sort of one of the conceptually simplest way, but sort of computationally more expensive way, is actually to look at a wave function that now, instead of being given by a single determinant, is given by a combination of determinants with different coefficients, in which, say, the determinants have been constructed with sort of a number of orbitals that include also excited orbitals. Our original Hartree-Fock determinant, say, for iron was given by the 26th lowest solution, and this is it. But then you could add a second term that contains 25 of those 26 lowest solution, and then one excited states. Or you could do sort of a number of things, but basically you could increase the variational flexibility of your problem. And the more flexible you become, the closer you get to the right solution, but you pay an enormous price for this. And sort of, this general approach would be called configuration interaction, that has actually this horrific scaling of n to the 7th. And so you can really do it for 10 electrons, but you can't do it for 11 electrons on sort of your best computer. Probably now we can get to 15 electrons or so. And I think with this, I'll conclude. So this was a panorama on Hartree-Fock methods. One of the best books is the Jensen book of computational chemistry in the literature. And then with next class, we'll start looking at density functional theory, and again, the Nobel Prize for Chemistry in 1998. Next Tuesday is sort of being Monday President Day. We'll have sort of on Tuesday, Monday schedule of classes. That means in practice that we have no class. So you have time until Thursday of next week to brood over this. I've posted a few readings on the website. If you sort of are really sort of wanting to know more about density functional theory, one of those readings is the Konov paper on fundamentals of density functional theory. And if you want to know more of Hartree-Fock that we won't really see anymore in the rest of the class, you should go to one of the references. And otherwise, see you next Thursday.